Welcome to CPE350, Chapter 8, Binary Mass Transport with Diffusion and Advection. This is the last section in our chapter in which we cover convection and boundary layers. So we've already seen that the total mass flux combines advection and diffusion. And so our expression that we've previously derived for total mass flux is for species A, rho A times the velocity of A, and that's a velocity specific to the species A. This is also equal to the combined diffusive flux with the advective flux. So JA is the diffusive flux and rho AV is the advective flux. And so that's the total velocity of the mixture, and that's what we actually measure as V. Rearranging, we get that the diffusive flux is equal to rho A times the difference between these velocities of just species A and the total mixture velocity, V. And this is kind of a strange way of writing things, but what we see is that the diffusive velocity is relative to the total velocity. And so to visualize this, let's track a single molecule of A in a diffuse situation where the bulk of the fluid comprises B. So the mass fraction of B is just about 1. So here's a tube, and as we track a particle of A over time, we see from the outside that A appears to move with the bulk velocity of the fluid. Now, if we were to float a sensor within the mixture traveling at the same velocity, the bulk velocity V, we would see that we need to derive a time Now, if we float a sensor in the mixture traveling at this bulk velocity V, we need to derive a Now, if we float a sensor in the mixture with traveling at velocity V, we define a coordinate axis that is local to the sensor. So no matter where in the solar system the sensor goes, X is always going to be that left-hand side edge. So if we do that, we see that the sensor follows the particle, it tracks the particle, and what the sensor is actually measuring is the diffusivity in the X direction of the particle. And what that would look like if we were able to track it on the order of angstroms is we would see that the X position is going up and down, sort of randomly. It's a random variable because diffusion is random. And that's because there's no concentration gradient in the system. If there were a concentration gradient, we would expect to see that the diffusivity increases across the length of the tube, depending on which way the concentration gradient is going. But basically, the whole point of this is that the frame of reference determines what you measure. And so when you write that the diffusivity is with respect to the frame of reference of the velocity of the bulk fluid, you're looking at just the velocity of diffusion. So VA minus V is that velocity of diffusion. Next, we look at convection at a solid interface. And this is given by this equation. And physically, if we look at this, a potential scenario could be a pure fluid of B flowing over a pure solid of A, which is soluble in B. And we see that at A diffuses into B as B advects over the surface of A. So NAX is our mass flux of A, kilograms per meter squared per second. Rho is the total density of the mixture. Again, it's a binary mixture, so just A and B, kilograms per meter cubed. And Km is our mass transfer coefficient. It has the same units as velocity. Omega AS is the mass fraction of A at that solid fluid interface. And omega A infinity is the mass fraction of A in the bulk of the fluid, and in this instance, we've given that omega A infinity is equal to 0. So now, if we want to derive an expression for molar mass convection, we derive the mass expression by the molar mass, Ma. And on the left-hand side, the units work out such that if you divide, you get something in terms of moles of A per meter squared per second, which is just the molar flux that we want, so we give that capital NaX. And on the right-hand side, if we look at the product of rho with omega A divided by Ma, we see that the units work out such that if you cross all the dimensions, you get something that has the units of moles of A per meter cubed. That's a concentration. And so we're looking at something, the concentration of As minus the concentration of A at infinity. So that's our molar mass convection term. Now we look at the effect of boundary layers in a flowing fluid over a solid surface. So if we look at the velocity profile, we see that at some distance y from the surface of the solid, there's a point where the velocity is almost the same as the velocity at an infinite distance from the surface. And the specification we require is 99%. So the boundary layer thickness for the velocity is the y value when the difference between v infinity and vx at that y position, normalized by v infinity, is 0.99 or 99%. So you've almost reached the bulk velocity of the fluid. You're just about there. If you had to wait until you were at the entire bulk, similarly, if we look at the y distance when the concentration of A tends to saturate, we define the boundary layer for concentration, which is just when the difference between the concentration of the pure solid and the concentration of A at an infinite distance from the solid in the bulk, normalized by that A concentration at the solid, is about 99%. Again, these are not hard and fast definitions. It's just a rule of thumb to sort of define where the boundary layer lies. Finally, we're going to look at the Sherwood number, which is defined as the ratio of the convective rate of transfer to the diffusive rate of transfer, roughly. And we have that when the Sherwood number is small, we have a small velocity in the surface. When the Sherwood number is small, that means there's a small velocity at the free surface, and that gives us a small value of Km, and consequently, we're in a convection limited regime. So diffusion is fast relative to convection. Conversely, when we have a large value of the velocity at infinity, we have very fast advection. Km is relatively small, and we're in a diffusion limited regime. And so this is quite analogous to the BO number that we saw in thermal transport. This concludes Chapter 8. Thank you for listening, and I'll see you for the next chapter.